Okay, so in this chapter, we are going to look at the fundamental theory of orthogonality and the second fundamental theorem of linear algebra. And we're going to relate the two subspaces in Rn and two subspaces in Rm. And we're going to see that they are actually orthogonal to each other. And we are going to give another way of stating the fact that if we're going to give an alternative way or stating the fact that if Ax is B is solvable, if B is in the column space, by stating or by proving that since the left null space and the column space are also orthogonal or are orthogonal complements, therefore every vector in the left null space is orthogonal to every vector in the column space. So Ax is equal to B is solvable, meaning if B is in the column space of A, this is the same thing as saying that you find a vector Y and you say the dot product of Y and B is orthogonal. So if that is true, then you say the solution of Ax is equal to B exists. So this is what we want to do today. So let's start with this chapter. Let's continue with the chapter. So the fundamental theorem of orthogonality. So fundamental theorem of orthogonality. The fundamental theorem of orthogonality is row space, which, if you recall, is written as a row space of matrix AMN, is orthogonal to null space, or maybe I write so that you recall, to null space, which is written as this one, and column space is orthogonal to left null space, which is null space of A transpose. So this is a fundamental theorem of orthogonality, and we can prove this very easily. So the proof is A times X is actually, you have row 1 here, row 2 here, and this is the row M over here. Okay, and then you have X over here, so X over here, and then you say that this is equal to 0. So this is how you find X in the null space. So what you're doing is you're saying actually this row into this X, and this is, by the way, equal to a string of zeros. So you say this row into this X equals this one. So you say, so, and obviously this row into this X equals this one. So you say the row I dot with vector X is going to give you 0. So this implies, and this is true for all I. So you say rows of A are orthogonal to X, but where is X? To X, which belongs to the null space of A. So this simply means, but rows of A give you what? So combination of these rows is the column space, is the row space of A. So this means the column space of the row space of A, or the column space of A transpose, is orthogonal to the null space of A. Right? Also, same approach. We have Y transpose into A equals 0. So this implies that this is a row vector. So this is M by N. Obviously, this is 1 by M. This cancels. So this is 1 by N. So we have Y1 y2, and then I have column 1, column 2, and this is equal to column n, right? Because it's m by n, and this is equal to 0, 0. So again, I do the same thing. So I say this is y, or maybe I write this y in the same way. So I'm sorry. So this is some y transpose. Okay. So this vector times this column vector is equal to this one. So same here. So for ith column or for ith column, we have y transpose dot column I equals the ith 0 here. So this, and this is true for all I. This implies y is orthogonal to columns of A, but combination of columns of A, combination of these columns is the column space of A, and where y belongs to. So y belongs to the left null space. So you say, so since y is orthogonal to combination of all these columns which generate the column space, so this implies the column space is orthogonal to the left null space. Okay. And there is another proof. So another way of proving this one. So another proof is if x belongs to the null space of A, this implies Ax equals 0, right? If V belongs to the row space of A transpose, this implies A transpose V equals some Z. So sorry. So maybe I write this. If V belongs to the row space, this implies V is a combination of rows of A, which implies V is some A transpose Z, right? So this is the columns. So this is actually the column space of A transpose, but the column space of A transpose is same as the row space of A for any Z, for some Z. Maybe I don't write for any Z, for some Z. So now V transpose X equals what? So V transpose X is A transpose Z transpose X. If this dot product is 0, this means V and X are orthogonal. But where is V? V is in the row space, X is in the null space. So if they are orthogonals for any X or V, so this means both the subspaces are orthogonal. So this is equal to. So whenever we have A B transpose, this is Z transpose. The order is reversed. A transpose is A and X. But what is AX? AX is equal to 0 because X is in the null space. So this is equal to 0. Or this implies null space of A is orthogonal to the row space of A or the column space of A transpose. Okay, so let's look at an example. So A is equal to 1, 2, 3, 1, 2, 3, 3, 6, 9, and we can easily see if this is A1, this is A2. So A2 is 3 times A1. So there is only one independent column. Okay, so if there is only, it implies only one independent column. So which means rank equals 1 equals one independent row. One independent row. And what is that independent row? This is the first one. The first one is the independent row. So I don't have to do any echelon form, reduce this A to an echelon form. Or if you want, I could do that. But in any case, let's do that. So I do minus 2R1 plus R2 minus 3R1 plus R3. If I do that, I'll get 1 and 3. Minus 2 plus 2 is 0. Minus 6 plus 6 is 0. Minus 3 plus 3 is 0. Minus 9 plus 9 is 0. So there is only one pivot. So this is the pivot. If this is the pivot, so there is only one pivot variable and there is one free variable. So this implies one free variable. Since there is one free variable, this implies the dimension of null space of A. Dimension of null space of A is also 1. Why? Because n minus r is 2 minus 1 equals 1. So before we find the dimension of the null space, let's find the column space. So the column space, so 1 here corresponds to this column here. So this is the independent column. So column space of A is generated by 1, 2, 3, and this is a subspace of of R3. Okay, and the row space of A is generated by so this is the column, so this is the row. So I can simply pick this row because the row space of U or R is the same as the row space of A, because when you do the elementary row operation, the row space is not changed. It's just a combination of the rows that you're doing. So whether you pick this row or you pick any other row, pick this row or the corresponding row in A, which is by the way the same. So doesn't make a difference. So this is 1, 3 is a subspace of R2. Okay. Obviously, these two are not orthogonal. The null space of A is generated by. So we have only one free variable. So it's two-dimensional, and that one free variable is 1 over here. Is a subspace of R2, and this 3 comes over here on the other side. Since it's on the left of the equal to sign, this becomes a minus 3 over here. Now whether these two are orthogonal or not, and obviously these are orthogonal because 1 and 3 dot product with minus 3 and 1 equals 0. So this is orthogonal. Okay, and the left null space, so the left null space of AT is generated by, and what is the dimension here? So the dimension here is, m minus r. M is 3, so it's 3 minus 1, which is equal to 2. So there are 2. It's generated by, there are 2 vectors, and these 2 vectors are actually three-dimensional. So 1, 2. So any combinations. So if I have a vector y here, combination with rows will give me the left null space. So let me do the echelon form for A transpose. So A transpose is equal to 1, 3, 2, 6, 3, 9. 1, 3, 2, 6, 3, 9. Then I do minus 3 R1 plus R2. If I do that, I'll get 1, 2, 3. I'll get minus 3 plus 3 is 0. Minus 6 plus 6 is 0. Minus 9 plus 9 is 0. So this is the only pivot. Okay. Now there are 2 free variables. So implies two free variables here, two free variables. Since these are two free variables, this minus this 2 is going to go here minus 2. This 3 is going to go here minus 3. Since there are two free variables, this is 1 alternately, 0 here, 0 here, 1 here. So these are my free variables. Free variables. And this is of dimension 2. So let's go back here and check with this one. So minus 2, 1, 0 with dot product with this one. So minus 2 into 1 is 2. 1 into 2 is 2. So minus 2 plus 2 is 0. Minus 3 into 1 is minus 3. 0 has no contribution. 1 into 3 is 3. So minus 3 plus 3 is 0. So this is indeed the left null space. You can also check. So these are two vectors, 1 and 2. So this dimension is 2. So two free variables. So this is the first one. This is the second one. So these are the vectors in the basis set that generate this space. And you can also check A times this vector will give you 0, and this vector times, or A transpose times this vector, or this vector times A will also give you, the transpose of this vector times A will also give you 0. So you should also always check your result whether your AX is equal to 0 is satisfied, or Y transpose A is equal to 0 is satisfied. This is the check. So you should always check whether your answer is correct or not. Okay. Good. And this is the plane. So this is dimension is 2. So this implies a plane. So a plane and a line are orthogonal, but a plane and a plane cannot be orthogonal. This is again the result that we did before. Okay. So let's define. Let's define the orthogonal complement. So definition. So definition of the orthogonal complement. So we say, given a subspace V of Rn, given a subspace V of Rn, the space of all vectors, the space of all vectors orthogonal to V is called the orthogonal complement, is called the orthogonal complement. This is not IMENT, this is EMENT. It's called the orthogonal complement of V, and is denoted by V perp. This is V perp. This is called V perp, PERP. Just for the perpendicular thing, this is just V perp. Okay. So this implies the orthogonal complement of the null space is the row space, and the orthogonal complement of the left null space is the column space. And this is the second part of the fundamental theorem. So fundamental theorem of linear algebra part 2. First we said there are two subspaces which are orthogonal, but now we say that these are also orthogonal complements. Linear algebra part 2, and this is the null space of A is orthogonal complement of row space of A in Rn, and the left null space of A is orthogonal complement of column space of A in Rm. Now this is what I've been talking about since lecture 1. Now Ax equals b requires, for this to be solvable, we requires b to belong to the column space of A, or this implies from this definition, or B should be orthogonal to the left null space of it. Is this all right? So an alternate way of saying is, thus Ax equals B is solvable if and only if y transpose B equals 0, where y transpose A equals 0, or y belongs to the null space of A transpose. Right? Or y belongs to the left null space, not null space of the right null space or the left null space of A transpose. So only when dimensions are right, or spaces, orthogonal subspaces are necessarily orthogonal complements. So if you recall, in chapter 2 we had a figure, and let me draw that figure again. But so you have we have this figure here. This angle is 90 degrees. This angle is also 90 degrees. This is called the column space of A. This has dimension equals to R. This is the left null space of A. The dimension here is m minus r. This is rm. This is rn. This is the row space of A. This is the left null space of A. This has dimension equals to n minus r. This has dimensions equals to r. So you have some x r over here. This is xn over here, right? This is xn over here. This is, by the way, 0 here. This is, by the way, 0 here. So this vector here is x. Okay, so x is xr plus xn. This xr maps to this vector over here. This is b. This is some b. You say a times xr equals b. This vector also maps to this one. This is a times x equals b, and this vector maps to 0, a times xn equals 0. So the only difference between the figure of chapter 2 and chapter 3 is now we have spaces which are at right angles instead of just lines that we had before. So what this picture is telling you is that every matrix transforms its row space onto its onto its column space, onto its column space. This is what every matrix does. So any B, so whatever this, just like this component XR and XN, so you have this B here and you have some Y over here, and these are also orthogonal. So instead of saying that B belongs to the column space of A, you can also say that B dot Y is 0, where Y belongs to the left null space. This is what we meant when we wrote the second fundamental theorem over there. Okay. So let's now answer, before we answer the question with what happens, is Ax equal to B solvable even if B is not in the column space? Before we answer that question, let's look at some projections. So cosines and projections onto lines. So let's look at cosines. So part of this probably you have already done in high school, IFSC or A levels, and part of it may be new to you. Cosines and projections onto lines. Okay. So we want to connect inner products to angles and also transpose. So what we want to do is, the goal here is to connect. So this development of theory is just to show what happens if B is not in the column space. Can we still get a solution or not? So the short answer is yes. So to connect into inner products to angles and also transposes, So let me draw a picture first. So we'll come back to this picture during this lecture and maybe later on. So this is some line. Let's call this vector A. This is some vector B. This is some vector B. And this is its projection onto the line. Right? So this is the projection onto the line. This we say is the angle theta. And this point, this one is P. So P is this vector up to this point, which is the projection of the line of the vector B onto this one, where we say A and B are not orthogonal. So A and B are not orthogonal. Okay. So this is E. So this vector is E, which is obviously B minus P. Right? So E is B minus P, this is P. P is the projection of B onto A. There is a projection of B. So P is the projection. Actually, this point is a projection, but this vector is in the direction of A. So this is the projection of B onto a line through A. We can easily generalize this to a subspace, because a subspace can also be a line. So we can always say, okay, this is the projection of B onto a subspace. So we'll do that in a little while. But before we do that, so point B, so let me write it for you. So situation is same when we are given a plane, when we are, so this is, assume that you're in a room and the plane is the floor and your point B is in the space, in the three-dimensional space, obviously above the floor. And if you visualize that picture, then this statement is going to be much simpler for you, much easier for you to comprehend. So situation is same when we are given a plane, or any subspace S, or any subspace S instead of a line, Point P is the projection of B point P is the projection of B onto the subspace, onto the subspace, onto the subspace, maybe which goes through A. So a perpendicular from B to S onto the subspace S. Let me call this S. So a perpendicular from B to S meets subspace. So please kindly keep this picture in mind when we are discussing the projections. So assume that you are in a room where the floor is your subspace, or a line on the floor is a subspace, and there is a point in the three-dimensional space which represents the end point of B, where B is from the corner of your room to there, where the corner is the origin. So a perpendicular from B to S meets subspace at P, and this is the geometrically gives distance between B and subspace S, and you can see this is the shortest distance because it's a perpendicular. Okay, so the question that somebody or maybe you want to ask is, so the question is, does this projection actually arise in practical applications? And the answer is yes, in practical application. Otherwise, there's no need of studying this this problem in practical applications. And the second is, if we have a basis for S, is there a formula? Projection? Obviously, if we can do that, then life is much simpler for projection P. So this is actually related to the problem of least square solution. Least square solution. So this is called LS, least square solution to an overdetermined systems, where you have number of equations much larger than is greater than the number of unknowns. Solution to an overdetermined system. Don't worry about over or underdetermined system. As long as we know the theory, we can always figure out whether the solution exists or not. So the answer to the first part is yes. Here, for example, B contains some experimental data. Experimental data and has errors. And is not found in subspace S. That is B is not a combination of the bases of subspace. Is not a combination of basis vectors of S. This implies equations are inconsistent. Equations are inconsistent and ax is equal to b has no solution, and ax is equal to b has no solution. Doesn't look nice then. Also, least square method. So what does least square do? So least square method selects p as the best choice, as the best choice for an equivalent b, actually as the best choice to replace p, because p is in the subspace, so obviously ax equal to p should have a solution. So least square method selects p as the best choice, and this is actually the regression analysis. This is the regression, fancy word that they use, economists and statisticians. Regression analysis in economics, in economics in economics and statistics, statistics. So least square solution, the regression analysis is a fancy word for the least square solution of ax equal to b. So let's develop this theory and see how can we find p when a is a line or when a represents the subspace. So inner products and cosines, inner products and cosines. So we have last lecture two, where we had this vector here, this angle is theta, this vector here was 1 0, if you recall. Then this thing is simply cosine of theta, this is sine of theta, right? Okay, good. Let's draw another picture here. This is origin, this is origin. Let's draw a vector here. This is vector A, and A has two components, A1, A2. So somewhere over here is A2, somewhere over here is A1. This angle is alpha. This vector is B, and B, which is equal to B1, B2. Okay. And this length is A, this length is B, and then we have a vector from here to here, and this is B minus A or A minus B, doesn't make a difference. And this angle is beta, and this angle between the two is theta. So theta is beta minus alpha. Okay, I think this is all right. This is x, this is x, this is y, this is y. Okay, so let's do some geometry. What is sine alpha? So sine of alpha is simply this A1, A2 over this length, So sine of alpha is A2 divided by the norm of A, right? Okay. And what is cosine alpha? Cosine of alpha is obviously the base, which is A1. There is no vector, it's not a vector. A1 divided by the magnitude of it. Good. What is sine beta? So sine beta is again simply B2 divided by the norm of B, and cosine beta is B1 divided by the norm of B. Okay. And cosine theta is cosine of beta minus alpha, which is equal to cosine beta alpha plus sine beta sine alpha, which is equal to cosine beta cosine alpha is a1 b1 over a b, and sine beta sine alpha is denominator is the same, so I have plus a2 b2. But what is a1 b1 a2 b2? This is simply a transpose b, because this is b, this is b, this is a. If you do transpose a1 into b1, a2 into b2 plus a2 into b2, that's the inner product, and this is simply, and this is also the inner product. I can also write this in terms of the inner product, but let's write in terms of the norm, a norm b norm. So this is cosine of theta. Okay, what is the law of cosine? So we can actually prove the law of cosine from here. We can actually prove the law of cosines from here. So what is the law of cosines? So law of cosines, if you recall from your trigonometry, this is cosine of the angle between the two vectors is this norm plus this norm minus twice these norms times the cosine of the angle between the two. So let me see if I can prove this one. So law of cosine is actually b minus a norm squared is equal to what? This is b minus a transpose into b minus a. This is not b minus a into b minus a transpose, because that will be a vector. So this is a scalar, so this is a scalar. Since this is a scalar, this is b minus a transpose into b minus a. So if I expand this one, so a plus b transpose is simply a transpose, a transpose plus b transpose. There's order is not reversed. So this is b transpose into b transpose. So this is b transpose into b transpose minus plus a transpose into a minus a transpose into b minus b transpose into a. Now a transpose into b is the same as b transpose into a. There's not difference. There's no difference because both are scalars, and you'll get the same answer. So this is equal to norm b squared plus norm a squared minus 2 times a transpose b. Why? Because a transpose b is equal to b transpose a. But this is equal to what? So this is equal to b magnitude plus b norm squared plus a norm squared minus, what is a transpose b? A transpose b is this one times this one minus 2 a into b into cosine of theta, right? So this is a familiar law of cosines. So that if you are interested in this length or in this length, then this is simply this length squared plus this length squared minus 2 times these two lengths times the cosine of the angle between the two, which is which we can also find from these vectors. Okay, good. Okay, so let's find the projection onto a line. So projection onto a line. So projection onto a line is point P. Point P is some multiple of A. Is some multiple of A. That is, let's call that is P is equal to some x hat times A. So let me go back to that figure. So let's go back to this figure. So this P, this is x on, sorry. So this P is equal to some x hat times A vector, times A vector. So it's the projection. So this vector is A. So this portion is simply x. So this portion is x. So the length of the projection is x, and it's in the direction of A. So let's go back here. Okay, so point P is a multiple of A, that is P is x hat. So x hat is the length of projection of B onto A, and obviously it's in the direction of A. Okay, so line from B to closest point P is orthogonal to A and is B minus P, which is E. So again, go back here. So this line B minus P is orthogonal is at P, at this point P is orthogonal to A, right? So we say, so keep that picture in mind. So we say B minus x hat into A dot A. So this error, so this is the error is 0, right? Or B minus x hat A A transpose into this one equals 0. It's one and the same thing whether I take the transpose here or transpose here. So x transpose y, just remember this thing. Remember, x transpose y is equal to y transpose x. We are write it again. So x transpose y, so whether I write A transpose B or I write B minus x hat A whole transpose into A, this is one and the same thing, nothing has changed. So if I do that, so if I multiply out, I'll get x hat, which is this is a scalar, by the way. This is scalar. So x hat into A transpose A equals A transpose B, or this implies x hat is simply A transpose B divided by A transpose A. But what is A transpose A? This is simply A transpose B divided by the normed square of A. Everything is scalar fifth. So this is a scalar. So this is a scalar, and obviously this is also a scalar. Okay, or P equals x hat A, which is equal to A transpose B over A transpose A into A. So this thing is a scalar and this is a. So this is also a scalar. So I can write A on this side or I can write A on this side. In a little while, I'm going to write side to see what happens, and then we'll see what's going on. Okay. Or maybe I can do that. Or this is also equal to A transpose over A transpose A. This is a scalar, and this B is then here. This, by the way, we'll call this a projection matrix. This is a scalar, but this is a rank 1 matrix. This is a rank 1 matrix. This is a rank 1 matrix. This is a rank 1 matrix, and this will be equal to some P times B, and this P is called the projection matrix. Okay, so let's hold this thought for a little while, and then we'll come back to this one. But let's look at the error now. So let's look at the error. So what does the error tell us? So E magnitude, E norm square is actually B minus x hat or B minus P norm square, which is equal to equal to B minus P is X hat A, so I'll write this as A transpose B over over A transpose A, maybe A transpose A into A norm square. Okay, and this is the distance. Obviously this is greater or equal to 0, and this is also greater or equal to 0. I'm not going to write this greater or equal to 0 all the time, but just to tell you that this is a distance, so this is the norm square, so obviously this is a positive number, a positive number, a positive. If I expand this one, this will become, so this is equal to B vector minus A transpose B over A transpose A into A whole transpose into B vector minus A transpose B over A transpose A into A vector. Just remember that this is a scalar. This is a scalar, so we don't care. Okay, so if we expand this one, so B transpose into B is B transpose into B minus, or this one into this one is plus, this is whole square, plus A transpose B whole square over, maybe I write A transpose A whole squared like this one, and this is A transpose A, so A transpose A, so actually this cancels with this one, and then I have minus, and this is a scalar, so this minus 2A transpose B into A transpose B over A transpose A, and this one becomes, so this is minus 2A square, this is plus A square, same thing here, so I can write this as B transpose B into A transpose A minus A transpose B square. Everything is scalar, divided by A transpose A divided by A trans, and this is greater or equal to 0, or this implies B transpose B into A transpose A is greater or equal to A transpose B square. Or if I take square root of both sides, or A transpose B, if I take positive square root, this is less than equal to, this is a norm squared, so this is actually norm squared, and this is also norm squared, so this is actually A norm B norm. This, by the way, is called the Schwartz inequality. Schwartz, this is called the Cauchy-Schwarz Woniakowski inequality. Probably more familiar with, probably you're more familiar with the Cauchy-Schwarz thing. Or this is also equal to, but what is A transpose B? Or recall cosine of theta is equal to A transpose B divided by A B. So A transpose B is, so A transpose B divided by this one, so if I divide, so these are positive numbers. If I divide both sides, divide both sides, so I'll get A transpose B magnitude over A B. This inequality is not going to change. Why? Because these are positive numbers. This is 1. But what is this thing? Or cosine of theta is less than equal to 1. Right? In R n. So only if, so equality holds if B is a multiple of A, meaning it's either in the same direction or the opposite direction, then theta is either 0 if it's in the same direction, or theta is equal to 180 degrees, that is in the opposite direction. In both these cases, this implies E is equal to 0. There is no error because B lies in the column space. Okay, so let's look at one example. So project B, which is 1, 2, and 3 onto a line through A, which is 1, 1, 1, right? So we know x hat is A transpose B over A transpose A, which is equal to A transpose B is 1 plus 2 plus 3. So 1 into 1 plus 2 into 1 plus 3 into 1 divided by 1 into 1 is 1 square plus 1 square plus 1 square. So this is 1, 2, 3. So 1 over 3, 3, 4, 5, 6 into 6. So this is 2, or P is equal to x hat A, which is equal to 2 times A, which is equal to 2, 2, 2. And what is cosine of theta? And cosine of theta, if you recall, cosine of theta, the first figure that we drew, this is simply the norm of B divided by the norm of B. The norm of B is 2 square plus 2 square plus 2 square under root divided by norm of B is 1 square plus 2 square plus 3 square, again under root. So this is 4, 8, 12. So this is under root 12 over 9, 10, 14. Or I can write this one as under root 4, 2, 7, 2, 6, 6 over 7, 6 over 7. Or I can write this as if I multiply and divide by 6, 6 over 6 is 36. So 6 over under root 42, which I can write as 6 over 42 is 14 into 3. So under root 3 under root 14. Right? So this is how you can find the angle between the two. And let's look at the projection matrix. So recall P equals x hat A, which is equal to A transpose B over A transpose A into A, which is equal to A into A transpose over A transpose A into B. Why? Because A transpose B over A transpose A, this is a scalar. If you do that, now A transpose into A into A transpose is a matrix of rank 1. This we have seen from chapter 2, and we say, so this implies P is equal to some P into B. This one is some P, this where matrix P, which is called the projection matrix, is actually A into A transpose over A transpose A. Also note, P transpose is A into A transpose over A transpose A. This is a scalar. So A entire, which is equal to P. So this is a symmetric matrix. Okay. So maybe Maybe we do an example before we end today's lecture. So the example is matrix. Find the matrix. So find the matrix. Find the matrix that projects onto a line through A, which is 1, 1, 1. So we know that matrix is this one. So P is, this implies P is A transpose, A into A transpose, A into A transpose over A transpose A, which is equal to, where this implies A transpose A is simply 1, 1, 1 into 1, 1, 1. So this is 1 into 1 plus 1 into 1 plus 1 into 1, which is equal to 3. And A transpose is, so this is 1 over 3 into 1, 1, 1 into 1, 1, 1, which is equal to 1 over 3. So every row or every row is a multiple of this row, every column is a multiple of this one. So we have 1, 1, 1, 1, 1, 1, 1, 1, 1. Obviously rank is 1. This implies rank is 1, because there is only one independent row or there is one independent column, because only one independent row or column. Okay, good. Also note, P square is equal to P. And why is that? So this implies this is because A transpose over A transpose A into A transpose over A transpose A. So this is equal to A transpose A, which is a scalar, into A transpose divided by, this is A transpose A into A transpose A. So this is A transpose A whole square. So this cancels with, this cancels with this one, and I'm left with A transpose. Because this is a scalar, I can take it out of this side. So this is A transpose divided by A transpose A, which is equal to P. Okay, good. So now note P square B is projection of PB, however, PB is already on the line, through A. So this implies P square B equals PB, or this implies P square is equal to P. This is another way of proving P square is equal to P. Column space of A, or column space of P, basically. Column space of P is a line through A, which is 1, 1, 1. This implies rank equals 1. Null space of P is generated by, so there should be two free variables. So I can take this one and I can do minus row 1 plus row 2, minus row 1 plus row 2, and I can do minus row 1 plus row 3. If I do that, I'll get 1 over 3 outside, 1, 1, 1, and I'll get 0, 0, 0, 0, 0, 0. I can So this is my pivot. These are my free variables. And what happens is, so when I say generated by, so this is two free variables. So comma, comma. So two free variables means one here, 0 here, 0 here, 1 here. This one comes here, this becomes a -1. This one comes here, this becomes a -1. And if you see, both these are okay. So, and if you so this is negative here, this is negative here, and these are free variables. These are correspond to correspond to free variables. Free variables. These correspond to free variables. So these variables are here. These variables are here. These variables are here, and these free variables are here. And this is dimension is actually n minus r, which is 3 minus 1, which is 2. So this is one vector, this is the second vector. So every column, so column space is aligned through A. So this implies uh, every column is a multiple of A, and so is P, which is equal to X hat A, which is equal to P times B. Also, vectors that project to P is equal to 0, that project to P is equal to 0 means origin have to be orthogonal, obviously. Satisfy A transpose P equals 0. That is they are there that is these are orthogonal to A, and their component along the line is 0. That this implies they lie in the null, they lie in left null space, or this implies the perpendicular plane. Why? Because we know these two subspaces in Rm are, I think, orthogonal. Okay, so example. So this is example that the left null space is orthogonal to column space, and since P is symmetric, the column and the row spaces are same. Okay, so the last example before we sign off is projection onto theta direction, in xy plane. Is in xy plane, projection onto theta direction in xy plane is a line that goes through A equals cosine theta sine theta. This is the same as when we did the transformation, that there is nothing new. So P is equal to A into A transpose over A transpose A. A transpose A is 1, where A is 1. A norm squared is 1. So this is simply cosine theta cosine theta, cosine square theta, I think. Cosine square theta, cosine theta, sine theta, sine theta, cosine theta, and this is sine square theta. So if you compare this with linear transformations lecture on projections, you'll find it's exactly the same matrix. Okay, so that is all we want to do. Uh, we want to talk about projections. In the next lecture, what we want to do is we want to uh, we want to project this B onto the subspace, and then we want to in the subsequent lectures we want to orthogonalize the bases and see whether we have another form decomposition of the matrix A instead of A is equal to LU or not if the columns are independent. So let's stop here. If you have any questions, you can either email me or we can discuss on Mondays and Wednesdays. Thank you.